The National Electrical Code, specifically Section 240.21b2, permits the use of current transformers, or CTs, on each set of secondary phase conductors as a means of providing overcurrent protection for the secondary conductors of a transformer. This method is particularly applicable and often cost-effective in industrial supervised installations. To implement this protection scheme, several factors must be considered. Firstly, the CT themselves must be appropriately sized. The selection of the CT is crucial to ensure that they can accurately sense the current flowing in the secondary conductors and provide the necessary signal to the overcurrent relay. The ratio of the CT should be chosen such that the secondary current of the CT is within the operating range of the overcurrent relay for the expected range of primary currents. This involves calculating the full load secondary current of the transformer and then selecting CT with a suitable ratio to step down that current to a level that the relay can handle, typically 5 amps or 1 amp. Secondly, the overcurrent relay setting is a critical aspect of this protection scheme. The relay must be set to trip at a current level that is above the normal operating current of the secondary conductors to avoid nuisance tripping during normal load conditions. However, it must also be set below the ampacity of the secondary conductors, ensuring that the conductors are protected from overloads that could damage them or create a fire hazard. This setting requires careful calculation, taking into account the conductor size, insulation type, and installation conditions as specified in NEC Table 310.15. The relay should also have time delay settings that coordinate with other protective devices in the system to ensure selective tripping, meaning that only the circuit closest to the fault is interrupted, minimizing disruption to the rest of the electrical system. Thirdly, the installation of the CT is important for their reliable operation. The CT should be installed in a location where they are protected from physical damage and excessive heat. Heat can affect the accuracy of the CT and potentially damage them. The wiring connecting the CT to the overcurrent relay must be properly sized to carry the maximum current that the CT can produce under fault conditions. This wiring should also be shielded to minimize the effects of electromagnetic interference, which can cause false readings and potentially lead to nuisance tripping. The shield should be properly grounded to provide a path for any induced currents to flow to ground. Regarding the specific scenario of a 5 million volt ampere, 3-phase, delta ungrounded Y transformer in an industrial supervised installation, several additional considerations come into play. The delta ungrounded YA configuration presents unique challenges for ground fault protection. In a delta ungrounded Y system, there is no direct path for ground fault current to flow, which can make it difficult to detect ground faults using conventional overcurrent devices. However, this is where the overcurrent relay can be configured to detect unbalanced currents, which can be indicative of a ground fault. For the 5 million volt ampere transformer, it is crucial to perform a thorough short circuit study to determine the maximum fault currents that can occur on the secondary side. This study will inform the selection of the CT and the setting of the overcurrent relay. The fault current calculation should take into account the impedance of the transformer, the impedance of the secondary conductors, and the impedance of any connected loads. It is also important to consider the source impedance of the utility supply, as this can limit the amount of fault current that is available. In an industrial supervised installation, there are often sophisticated monitoring and control systems in place. The overcurrent relay can be integrated into these systems to provide real-time monitoring of the transformer's operating conditions and to provide alarms in the event of an overcurrent condition. The relay can also be configured to communicate with a supervisory control and data acquisition, or SCADA, system, allowing operators to remotely monitor and control the transformer. In summary, using CT and an overcurrent relay to protect the secondary conductors of a transformer is an acceptable method according to the National Electrical Code, and it can be a cost-effective solution for industrial supervised installations. However, it is essential to carefully size the CT, set the overcurrent relay, and install the equipment properly to ensure reliable and effective protection. Furthermore, when dealing with a delta ungrounded Y transformer, special consideration must be given to ground fault protection. The overcurrent relay can be configured to detect unbalanced currents, but a thorough short-circuit study is essential to determine the maximum fault currents that can occur on the secondary side. For instance, consider a scenario where the secondary voltage of the transformer is 480 volts. The full load secondary current can be calculated using the formula I equals S divided by the square root of 3 times V, where I is the current, S is the apparent power in volt amperes, and V is the voltage. In this case, I equals 5 million volt amperes divided by the square root of 3 times 480 volts, which equals approximately 6014 amps. The CT should be selected with a ratio that can accurately measure this current. For example, a CT ratio of 6000 to 5 amps would be a suitable choice. The overcurrent relay should be set to trip at a current that is above the normal operating current but below the ampacity of the conductors. If the secondary conductors are sized to carry 8000 amps, the relay could be set to trip at 7000 amps, providing a margin of safety. The time delay settings of the relay should be coordinated with other protective devices in the system. For example, if there are downstream circuit breakers, the relay should be set to trip after the circuit breakers have had a chance to clear the fault. This will ensure that only the circuit closest to the fault is interrupted, minimizing disruption to the rest of the electrical system. Remember to consult the National Electrical Code and other relevant standards for specific requirements and guidelines. It is also recommended to consult with a qualified electrical engineer to ensure that the protection scheme is properly designed and implemented. The selection of the appropriate CT ratio is critical for accurate overcurrent detection. The CT ratio is the ratio of the primary current to the secondary current. For example, a CT with a ratio of 6000 to 5 amps means that when 6000 amps are flowing in the primary winding, 5 amps will be flowing in the secondary winding. The CT ratio should be chosen such that the secondary current is within the operating range of the overcurrent relay. If the secondary current is too low, the relay may not be able to accurately detect the overcurrent. If the secondary current is too high, the relay may be damaged. The overcurrent relay is a device that is designed to detect overcurrent conditions and trip a circuit breaker. The relay consists of a current sensing element, a time delay element, and a trip output. The current sensing element measures the current flowing in the circuit. When the current exceeds a predetermined threshold, the time delay element begins to time out. If the overcurrent condition persists for longer than the time delay setting, the trip output is activated, which trips the circuit breaker. The time delay element is used to prevent nuisance tripping due to temporary overcurrent conditions such as motor starting currents. The trip output is a set of contacts that are used to trip the circuit breaker. The contacts are typically wired in series with the circuit breaker's trip coil. When the trip output is activated, the contacts close, energizing the trip coil and causing the circuit breaker to trip. The coordination of the overcurrent relay with other protective devices in the system is essential for ensuring selective tripping. Selective tripping means that only the circuit closest to the fault is interrupted, minimizing disruption to the rest of the electrical system. To achieve selective tripping, the time delay settings of the overcurrent relays and circuit breakers must be coordinated. The time delay settings should be set such that the device closest to the fault trips first, followed by the next device upstream, and so on. This can be achieved by using time current curves, which are graphical representations of the tripping characteristics of the protective devices. The time current curve should be plotted on the same graph to ensure that they do not overlap. The device with the lowest time current curve will trip first, followed by the device with the next lowest time current curve, and so on. In the case of a 5 million volt ampere transformer, the potential fault currents can be substantial. Therefore, it is essential to use high-quality CT in overcurrent relays that are designed for use in high-current applications. The CT should be capable of withstanding the maximum fault current without saturating or being damaged. The overcurrent relay should be capable of tripping the circuit breaker quickly and reliably under high current conditions. In addition to overcurrent protection, the transformer should also be protected against other types of faults, such as ground faults and phase-to-phase faults. Ground fault protection can be provided by using a ground fault relay, which is a device that is designed to detect ground fault currents. Phase-to-phase fault protection can be provided by using phase-to-phase overcurrent relays, which are devices that are designed to detect overcurrent conditions between phases. The use of current transformers to protect the secondary conductors of a transformer offers several advantages. Firstly, it provides fast and reliable protection against overcurrent conditions. Secondly, it is relatively inexpensive compared to other methods of protection. Thirdly, it is easy to install and maintain. However, it is important to carefully size the CT, set the overcurrent relay, and install the equipment properly to ensure reliable and effective protection. In the context of the National Electrical Code, Section 240.21b2 specifically addresses the protection of transformer secondary conductors. This section outlines the conditions under which overcurrent protection is required for secondary conductors and the methods that can be used to provide that protection. It is essential to consult this section of the NEC to ensure that the protection scheme is compliant with the code requirements. The NEC also provides guidelines for sizing conductors, selecting overcurrent devices, and installing electrical equipment. These guidelines should be followed to ensure that the electrical system is safe and reliable. In addition to the NEC, other relevant standards and guidelines may apply, depending on the specific application. For example, the Institute of Electrical and Electronics Engineers, or IEE, publishes standards for power system protection, and the National Fire Protection Association, or NFPA, publishes standards for electrical safety. These standards and guidelines should be consulted to ensure that the protection scheme is designed and implemented in accordance with industry best practices. The supervision aspect of the industrial installation is key to enabling this protection method. Supervised installations often have skilled personnel who are trained to understand and maintain the electrical system. This allows for more sophisticated protection schemes to be implemented, as the personnel can monitor the system and respond to alarms in a timely manner. The supervision also allows for regular testing and maintenance of the protective devices, ensuring that they are functioning properly. In contrast, unsupervised installations typically have less sophisticated protection schemes, as there is no one on site to monitor the system or respond to alarms. The protection schemes in unsupervised installations must be simple and reliable, and they must be able to operate automatically without human intervention. For the application of a 5 million volt ampere transformer, a comprehensive protection scheme is crucial to ensure the safety and reliability of the electrical system. The protection scheme should include overcurrent protection, ground fault protection, and phase-to-phase fault protection. The protective devices should be carefully selected and coordinated to ensure selective tripping and to minimize disruption to the rest of the electrical system. In conclusion, the use of CT and an overcurrent relay to protect the secondary conductors of a transformer is an acceptable method according to the National Electrical Code, and it can be a cost-effective solution for industrial supervised installations. However, it is essential to carefully size the CT, set the overcurrent relay, and install the equipment properly to ensure reliable and effective protection. Furthermore, when dealing with a delta and grounded Y transformer, special consideration must be given to ground fault protection. The overcurrent relay can be configured to detect unbalanced currents, but a thorough short-circuit study is essential to determine the maximum fault currents that can occur on the secondary side. Always consult the latest edition of the National Electrical Code and other relevant standards and guidelines, and consult with a qualified electrical engineer to ensure that the protection scheme is properly designed and implemented. This ensures the safety and reliability of the electrical system and protects against potential hazards. Consider, firstly, the importance of regular maintenance of the current transformers. These devices are critical for accurate current measurement, and their performance can degrade over time due to factors such as environmental conditions, contamination, and aging. Regular maintenance should include visual inspection of the CT for any signs of damage or deterioration, as well as electrical testing to verify their accuracy. The electrical testing should include ratio testing, which verifies that the CT is accurately stepping down the primary current to the secondary current, and insulation resistance testing, which verifies that the insulation of the CT is in good condition. Secondly, the proper grounding of the CT secondary circuits is essential for safety. The CT secondary circuit should be grounded at a single point to prevent circulating currents and to provide a path for fault currents to flow to ground. The grounding conductor should be sized according to the NEC requirements and should be connected to a reliable ground source. Improper grounding of the CT secondary circuits can create a shock hazard and can also interfere with the operation of the overcurrent relay. Thirdly, the selection of the appropriate overcurrent relay is critical for the performance of the protection scheme. The overcurrent relay should be selected based on the specific characteristics of the transformer and the electrical system. The relay should have adjustable settings for current and time delay, allowing it to be coordinated with other protective devices in the system. The relay should also have self-monitoring capabilities, which can detect internal faults and provide alarms. The overcurrent relay should be tested regularly to verify that it is functioning properly. The testing should include simulating overcurrent conditions and verifying that the relay trips the circuit breaker within the specified time delay. The testing should be performed by qualified personnel using calibrated test equipment. The documentation of the protection scheme is essential for maintaining the system and troubleshooting problems. The documentation should include a detailed description of the protection scheme, including the CT ratios, the overcurrent relay settings, and the wiring diagrams. The documentation should also include a record of all testing and maintenance activities. The documentation should be kept in a safe place and should be readily available to qualified personnel.